Welcome to Global Virtual School students. This is your first year chemistry class. I am Dr. Jalbano, and the topic for today from chapter number 3 is the valence shell electron pair repulsion theory. And students, valence shell electron pair repulsion theory explain the geometry of some simple molecules. After completing this topic, you will be able to predict the shapes of simple covalent molecule using valence shell electron pair repulsion theory. Students, this theory was first of all suggested by Sedgwick and Paul in 1940 to suggest both of the scientists suggest the shapes, or you can say the geometry and of the molecules. According to them, these shapes and geometry depends upon the number of shared as well as lone pair of electron. Shared electron pairs are usually that participate in the formation of the bond that shared by two nuclei. So basically, geometry depends upon these shared molecules as shared electron as well as the electron which do not participate in sharing or in the bond formation, that are called the lone pairs of the electrons. But in 1957, Gillespie and Neumann proposed that the arrangement of atoms in a molecule, if a molecule consists of more than one atoms, and it is mainly determined by the repulsive interaction among all electron pairs. Friends, I will make you clear. Electron pairs mean both the bond pairs and the lone pairs. Lone pairs which do not participate in the bonding, while the bond pairs that are shared, that are the shared electrons that participate in the bond formation. Basically, according to Gillespie and Neumann, the geometry depends upon the repulsion between these lone pairs as well as the bond pairs. So because these are all the electrons, they have the negative charge, they have obviously the repulsive interaction between them. So according to them, their shapes or arrangement depends upon the repulsion among these electron pairs. And the basic postulates of valence shell electron pair repulsion theory are: first one, the electron pairs. Electron pairs, students, when we talk about the electron pairs, it means both the bond pairs, bond electron pairs and the lone pairs that are present around the central polyvalent atom. Polyvalent atom means atoms having greater valency, more than one valency. They are arranged in space as far apart as possible so that there is minimum repulsion between them. So according to the first postulate, the electrons that are surrounding the atom, they are arranged in space that they have the maximum distance and the minimum repulsion between them. And the second postulate is a non-bonding pair or lone pair. Again, I am repeating, electrons which do not participate in the formation of bonds are called non-bonding pairs, or they also called the lone pairs. They occupy more space on the surface of an atom as compared to bonding pair. Space occupied means they have more influence because they are free, they are under the influence of one atom, while bond pairs electrons they have less influence, they have less exposed negative charge because they are fixed between two nuclei in a molecule. So lone pairs, they occupy more space as compared to bond pairs. Both the lone pairs, the third postulate is that both lone pairs as well as bond pairs, they determine the geometry of the molecules. So geometry of the molecules not only depends only one bond pair or lone pair, but it depends upon all types of, if it is bond pairs or the lone pairs. And the fourth one is the magnitude of repulsion. What is the quantity of this repulsion? Because atoms have lone pairs as well as bond pairs. If in some molecules they have the lone pairs, they have the bond pairs, then where will be the maximum repulsion and minimum repulsion? So the magnitude of repulsion between the electron pairs is, it is maximum in lone pair, then it's a little lesser in lone pair bond pair, and that is in bond pair band pair it is even lesser than lone pair bond pair. So lone pair electrons, they have more maximum repulsion, while bond pair and bond pair they have the minimum among them, and while lone pair and bond pair they have the intermediate repulsion. The two electron pairs of a double bond and the 3 electron pairs of triple bond, they contain a higher electron density, therefore they occupy more space than one electron pair of a single bond. Students, you are quite familiar about the single, double or triple bond. Single bond means formed by the sharing of one electron from each. One from each means 2 electrons pair, so they form a single bond. While a double bond is formed by sharing of 2 from each, so total of the 4 electrons. The triple bond is formed by sharing of 3 from each atom, so total of 6 electrons, or you can say the 3 bond pairs, because of course a triple bond it has more electron density as compared to double bond, double bond it has more electron density as compared to single bond. So they have triple bond have more influence as compared to double bond, and double bond has more influence or space as compared to single bond. However, they behave like a single electron pair in determining the geometry of the molecule. When we decide the geometry of the molecule, we consider a triple bond and a double bond as a single bond. We consider them that it is a single bond because just they have the bond between 2 atoms. They have only the difference of the electron density, otherwise they are between the 2 atoms. So we consider them a single bond while we determine the geometry of the molecules. So how to predict the shape of molecules? What are the steps to follow to predict the shape of the molecules? Its shape will be like this, or like linear or a triangular or some other shape. It has 4 steps basically. First of all, draw the dot diagram of the molecules. Like all of the atoms in the molecule, they have the valence electron. So the valence electron represented by dot, or they can also be represented by cross. So first of all, draw the dot diagram of the molecule. In the second step, determine the number of valence electrons surrounding the central atom. How much the electrons are surrounding on the central atom, only the valence electrons. Then determine the number of bond pairs and lone pairs of the electrons. So now determine how many bond pairs are there and how many lone pairs are there. Then determine the geometry distribution of the electron pairs so that they are as far apart as possible and they have minimum repulsion. So on the basis of presence of bond pairs and lone pairs, just check their repulsion among lone pair, or lone pair bond pair, or bond pair bond pair. Then just predict its shape will be like band, or like a pyramidal or tetrahedron, or linear or some triangular. So these 4 steps have to follow while predicting the shape of the molecule. Students, this one is the table to determine the shape of the molecules, and it is very important to understand this table. When you understand this table, you can draw the shape of any molecule. In first step, you can see here in this like total electron pairs. Total electron pairs means this include bond pair as well as lone pair. So first we have option if a central atom has total 2 electron pair. In this case, both of them are bond pairs. Students, here AB2, it means A is the central atom, like this. It is like a central atom. And B2, this stands for bond pairs. 2 means this central atom has 2 bond pairs and there is no lone pair. It has 0 lone pair. So if we represent this with ball and stick model, you know, beryllium chloride, BeCl2, AgCl2, CO2, they all have the linear shape. This central atom is A, and other atoms will be represented by stick. So when they have the 2 bond pairs, they will be maximum at this distance, like linear shape, because they have only this bond pair. Consider this is the beryllium, this is chlorine, this is chlorine. They are sharing two bond pairs, and they have no lone pair. So they will be as far apart as possible. They have maximum distance and they have the minimum repulsion among them. In this case, they have the linear shape. In this option, there is no lone pair. In second step, if there are 3 electron pairs, and it has further 2 options. Out of 3 electrons, all of the bond pairs, and there is 0 lone pair, there is no lone pair. So what will be the shape? A stands for central atom, and it has like 3 bond pairs. So 3 bond pairs that are at a maximum distance, this possible geometry will be like this, triangular shape. Because at this distance, they have the maximum dash distance and the minimum repulsion. All of are the bond pairs. So they have angle of like 120 degree, and this may be of angle of 180. And shape will be triangular, trigonal, planar. Because in this option, in this case, A is the central atom and all of the bond electron pairs are bond pairs. In this case, there is no lone pair. So we consider the option that central atom A has total of 3 electron pairs. Out of them, 2 are bond pairs and 1 is the lone pair. Lone pair that do not participate in the bonding formation, while bond pairs, they participate in the bond formation. So this will be like if this is the central atom and it has like 2 bond pairs and 1 lone pair. So due to lone pair, 2 bond pairs, if they are initially in this straight line, due to this lone pair and bond pair repulsion, this shape will be bent like this one. This is because of this lone pair. If this lone pair is not present, then this shape may be like linear. But because in the past lectures you have learned when there are multiple electron pairs like bond pairs and lone pair, and they have the repulsion. So lone pair is repelling more bond pairs inside, and here this is repelling more inside. So this bond angle reduces from 180 to a lesser degree. So this has the bent shape. In this case, like consider SO2. S has the central atom, it has lone pair, and with oxygen it has 2. In this case, in this example, it has double bond. But because in the past lectures you learned, while predicting the geometry, we consider double bond as a single bond. So it has a bent structure. Now we have the even a bigger molecule, like a molecule that has contained 4 electron pairs. And first we have the option like molecules that have the 4 electron pair and all of are the bond pairs and there is no lone pair. Example of such type of molecules is like methane, carbon tetrachloride, carbon tetrabromide, silicon tetrachloride. They all will have, what will be the shape? First look, this one is the central atom, carbon A, and this contains all the bond pairs. So these bond pairs, they have the minimum repulsion and the maximum distance. So their arrangement is like it's like a tetrahedron. Tetrahedron, it has like 4 faces. This one, consider this is the base, and this one is out of actually plane, so we can't draw as a 2D on the 2D. So in actual, these are the tetrahedron. They are at a maximum. They have equal bond lengths and bond angles. Like bond angles, they have a regular tetrahedron. It is 109.5 degree. This shape is tetrahedron. This shape is called tetrahedron or tetrahedral shape. Because at 109.5, they have a maximum distance and minimum repulsion. So their base is like a triangular and one is out of plane, that is like its apex, but they have, this is called a tetrahedron. This I will explain you in next slides with animation and 3D diagrams. Now we have other example, total 4 electron pairs, but out of them 3 are bond pairs and 1 is the lone pair. And consider this is like shape same, but now consider instead of 4th bond pair this has the lone pair like this. Due to lone pair repulsions, they have even bond reduces to 107.5 or 107. This is like a pyramidal. Like these angles are little reduces due to this lone pair repulsion. In this case there was no lone pair, but here is the lone pair. So due to lone pair bond pair repulsion, these angle further reduces to 107.5. For this we have the example NH3, PCl3, NF3, and now we have another molecule that is with 4 electron pairs, and out of them 2 are lone pairs and 2 are bond pairs. We have the example of water. This is the central atom. It has love. So now consider this is replaced by lone pair and this is replaced by lone pair. So due to lone pair repulsion, so they have more repulsion because it has 2 lone pairs. These angle further reduces to 104.5 degree, and it has the bend shape or angular shape because now have even more lone pair repulsion, lone pair bond pair repulsion, lone pair bond pair repulsion, and bond pair repulsion. So it has a bent, a V, angular shape. Now consider this. I'll draw for you CH4. Now I am applying all the steps to predict the shape of the molecule. Valence electrons in the carbon, first it has the 4 electrons, and the 4 electron will come from 4 hydrogen, 1 from each. So total are 8 electrons. 8 electrons means 4 pairs. 1 pair contains 2 electrons. Now consider this. This is the carbon. It has 1 hydrogen, 1 and this 1 hydrogen. And the 1 is out of plane, but I will draw this here like this. So it has 1 bond pair, 2, 3, 4. So total are 4 bond pairs. So first step is set valence electrons, total pairs. Out of them predict either these are bond pairs or lone pairs. So in this case all are bond pairs. So they have a maximum distance and minimum repulsion, and the angle is 109.5 degree. So this is tetrahedral shape like this. Consider carbon is in center, 1 hydrogen in this corner, 1 is in this corner, 1 this, and 1 hydrogen is this. So this is like a tetrahedron, regular tetrahedron. These all, it has 4 faces. First front face, this side face 2, and back face 3, and this the lower face 4. So this is called tetrahedron. Hopefully it is now it's clear for you. So hopefully tetrahedral shape of the methane will be clear. Now comes to the ammonia. Apply all the steps to predict the geometry of the molecules. NH3. Valence electron of nitrogen are 5 electrons. There are 3 hydrogen and 1 from each hydrogen electrons. Total are 5 through 8 electrons. So 8 electrons means it has the 4 electron pairs. Now look how many. 1 hydrogen, this 1 hydrogen, 1 hydrogen, and it has lone pair. So total bond pairs are 1, 2, 3. So 3 bond pairs and 1 electron pair. So total are 4 electron pairs. Now what is its shape? Now its shape will be like a tetrahedron, but in this case this tetrahedron is like a pyramid, because due to this lone pair, there is a repulsion between this and in this. So this angle reduces from 109 to 107 or 107.5 degree. So this is like a pyramid. It has a base like, and it is one apex. So it is pyramid. This I will also explain you with the help of an animation and a 3D diagram. And this is like this. Consider nitrogen is in center. There is one hydrogen. This one in this corner. This hydrogen, and this one is like, consider this is the lone pair. So due to this, it has a triangular pyramid. This base is like triangular, and this is apex because it has more influence. Now look at the animation.
An example of a molecule with 4 valence electron groups around the central atom is the ammonia molecule. 3 electron pairs form bonds between the nitrogen and hydrogen atoms. There is also 1 lone pair on the nitrogen. In accordance with the VSEPR model, electron groups point towards the vertices of a tetrahedron. Since one vertex is occupied by a lone pair, the 4 atoms of the molecule take the shape of a pyramid. The interbond angles, equal to 107 degrees, are close to the tetrahedral angle of 109.5. The reduction of the angle arises from the stronger repulsive effect of the lone pair.
So now it is the water molecule, H2O. So central atom is oxygen, and oxygen has, in the valence shell, it has 6 electrons, and hydrogen, 1 from each hydrogen. So total are 2. So these are 6 and 2, 8 electron. 8 electron means 4 electron pairs. Now look how many out of these electron pairs are bond pairs and lone pairs. So this is the oxygen, and like this hydrogen and this hydrogen, 1 lone pair, and this is the one other lone pair. So it means this has total 2 bond pair and 2 lone pair. So total are 4 electron pairs. But in this case, out of 4, 2 are bond pairs and 2 are lone pair. So now it has even more repulsion. Now it has lone pair repulsion, that is the greatest among lone pair and bond pairs. So, and there are also lone pair bond pair and lone pair bond pair repulsion. So due to these 2 lone pair repulsions and lone pair bond pair repulsion, this angle further reduces to 104.5 degree. In ammonia it was 107 due to 1 lone pair, while in methane there was 109.5, there was no lone pair. Due to 1 lone pair, angle reduces to 107.5, and due to 2 lone pairs, further reduces to 104.5. And this is like a bent shape, just a V shape. Look at this 3D diagram and then the animation. So due to this one is hydrogen, is oxygen, and here are the lone pairs. So this, due to repulsion, this angle reduces to 104.5, and shape is like bent or angular.
Now let us study a water molecule and try to determine its shape according to the VSEPR theory. 2 of the 4 electron pairs in the molecule are lone pairs. In the case of a water molecule, as in an ammonia molecule, the 4 electron pairs are oriented towards the vertices of a tetrahedron. This time, however, two vertices are occupied by lone pairs, which explains why a water molecule is non-linear or V-shaped. We can predict that the angle between the hydrogen atoms ought to be slightly smaller than the regular tetrahedral angle, and also smaller than in an ammonia molecule, because here the bonding electron pairs are repelled by two lone pairs. Indeed, this angle has been determined experimentally as 104.5 degrees.
So now we have even some more complicated molecules that contain more than 4 electrons. But in this is the example that contain total of 5 electron pairs. So out of these 5, all are bond pairs, and they have trigonal bipyramid shape like this. This is like example of this is the central atom, like PCl5P, and 3 like these. So they have an angle of 120, and 2 are above and below the plane like this, and in this case this has angle 90. So in this case few are of 90 degree angle and few of 120 degree, and they have like this one is triangular bipyramid. One pyramid is in above and one pyramid is like lower. So this is like a triangular bipyramidal. In this case, this base, like consider two pyramids are attached to each other, and those pyramid with a triangular base. While in case of a molecule with 6 electron pair, and out of 6 all are bond pairs and there is no lone pair, example is SF6. This is octahedral, and this is also like a pyramid, but in this case the base is like of a square. For example, this one is central atom, and this one angle, this, and like this. So this is like a square base, and they have the angle of 90 degree, and one is this in this plane and one is in this plane. So these all angles are of 90 degree. So one pyramid is in above, one is down, but in this case this pyramid has a square base. So two pyramids, and they have total of 4 above and 4 below. Total have 8 faces. Look at these animations. So all these angles are one, in this case 90, while in this case in AB5 types, and they have few of 90 and few of 120 degree. This one is triangular bipyramid, like central atom is this one, and one is of a regular like triangular. So these angles are 120, and one is above this out of plane, and in the plane these have angles with them of 90 degree. Look at this animation.
Bipyramidal arrangement. There are two sets of bond angles, 90 degrees and 120 degrees.
So now octahedral is like this one. There is the central atom, one atom, 2, and this is of like 90 degree angles, and one is out of plane, and here in this, these all are of 90 degree. So you can look, this is like two pyramids are attached to each other, but this central base is like a square. Look at this animation.
Octahedral arrangement, the bond angles equal 90 degrees.
So this was all about the shapes of the molecules on the base of valence shell electron pair repulsion theory. So now this is the question for you. Predict the shape of H2S. Its shape is just like shape of H2O. And also draw the diagram of BeF2. It is like BeCl2, BF3. It is like NF3 or BF3, BCl3, CCl4 is just like CH4, NF3 is just like NH3, H2O, and a few of them I have drawn for you. So apply these valence shell electron pair repulsion theory to draw the shapes of these molecules. Also mention their angles and their geometries. So this was all about the valence shell electron pair repulsion theory. Hopefully concept is clear for you. Just do practice and apply their prediction steps to predict the shape of the molecules. Our next topic will be valence bond theory. Valence bond theory is also to predict the shape of some simple covalent molecules.